All right, so we are going to be moving into the next section of chapter 5. We are going to cover section 5.2 and talk about logarithmic functions. So in the last video, you may remember me saying that there are certain exponential equations that we cannot solve by relating the bases, and there would be a new method we would have to learn. Well, we can't learn that new method until we cover this idea because this is going to be part of that new method. So in this video, we're just going to cover the basics of logarithmic functions, look at a few properties that might be beneficial to us, and then we'll kind of wrap this up. So for those who've never heard of this or want a refresher on it, knowing what a logarithmic function is our first topic. So a logarithmic function, all this is the inverse function of the exponential functions that we just looked at in the past video. So if you remember back at the end of chapter 3, we talked about what inverse functions were, about how you interchange your x and your y's or your domain and range, and then you would solve for the other one. Well, it's similar here. Anytime you find the inverse of an exponential function, it just turns into a logarithm. So what are the equivalencies here? Well, as you can see down here at the bottom, we talked about this form last time, where if you have b raised to a power equals a number or something, that's called an exponential equation. When we write it as a logarithm, because they're going to be equivalent to each other because they're inverses, the equivalent statement to that would be y equals the log of base b of x. Now, my easiest way, and what I usually tell students, and it takes a little bit of time to kind of let it click, but the easiest way to keep logarithms and exponentials straight and how they equal each other is that if you notice, the base of the logarithm and the base of the exponent should be the exact same number. So in this case, if I give you an exponent and say write it as a logarithm, the base will not change. It just moves to the base of the logarithm. Now, what does change is that since these are inverses of each other, since y is attached to the b over here, you'll notice that it has to flip-flop when you move to its inverse. So if y is attached to the base of an exponent, then you have to interchange this, and the base of a logarithm will have an x involved. Likewise, on the exponent, the x is by itself. When you interchange that and move to the logarithm, then y is by itself. And that's one of the easiest ways I know how to remember which is which. The base stays the same, but you flip-flop the x and y locations of each notation. And we're going to do a number of examples today to practice this, but that's what you'll hear me say a lot of, probably repetitively in this video. So let's do some conversions. So just making sure you're comfortable with both notations is I've given you two exponential equations. I would like us to rewrite them as logarithms using our conversion factor. So on the first one, we have a statement that says 3 squared equals 9. We all agree with that. But how do you write this as an equivalent logarithm? Well, what I will usually do is when I go from one to the other, I first identify the base of my exponent, which is 3. And I know based on conversion factors that that has to end up being the logarithm of my base, of my logarithm, in this case, my base. So I'll have log base 3. And then essentially, if I put the equal sign down here as well, you want to flip-flop the other two numbers. So since the 9 was by itself here, the 9 now needs to be attached to the 3. So the 9 goes with the logarithm. Since the 2 is attached with the 3, it needs to move to the other side of the equal sign, which would make it 2. And so 3 squared equals 9 is equivalent to saying log base 3 of 9 is equal to 2. All right. Similarly, we can do it for any of them. So we'll do one more. You've got 2 raised to the negative 3 is equal to 1/8. Write this as a logarithm. Well, if you identify the base of your exponent, which is 2, that means we're going to have a log base 2 Sorry, y'all, hang on. My thing is acting up. There we go. Sorry. So, like I was saying, you're going to have log base 2 because that has to stay the same. And remember, you're flip-flopping your two values. Since the -3 is attached to the 2, it cannot be when you move to the logarithm. So we move the -3 by itself. And since the 1/8 was by itself, and you're going to flip-flop these, the 1/8 now goes next to the logarithm. And so 2 to the -3 equals 1/8 is equivalent to -3 equals log base 2 of 1/8. You also want to be able to go the other direction because sometimes you'll have a logarithm and you want to write it as an exponent. So let's do that as well. Same conversion. On number 3, you've got log base 5 of 1 is equal to 0. Now we're going from logarithm to exponent here. So since the base of my logarithm is 5, that means the base of my exponent has to be 5 as well. Now, once again, you have to flip-flop the other two numbers. So since the 1 is attached to the 5 here, it needs to move to the other side of the equation by itself. And since the 0 is originally by itself, you have to bring it over as the exponent of your base. And you'll notice on one like this, you have just created a true statement. We should all know that 5 to the 0 is equal to 1, which is the equivalent exponent of the logarithm given. Now, something we'll see, and I think in the next video, is that you won't always have all the numbers given to you. So what if it's something like this on number 4? You've got log base a of x minus 1 is equal to 3. Well, once again, identifying the base of your logarithm, a, means that's going to be the base of my exponent. And you're going to flip-flop the other two parts. Since x minus 1 is attached to the a, it needs to move to the other side of the equation by itself. And since the 3 is by itself, it needs to move over and be with the a. So it becomes the exponent of a because you want this to be an exponential equation. And therefore, we have rewritten this logarithm as a cubed equals x minus 1. And so that shows you both different directions that you can do for conversions between exponential equations and logarithmic equations as well. All right, so kind of solving our first problem. So one thing that we use logarithms for is that they show up in different ways of you solving problems. So I've given you two examples here. I want you to finish the logarithmic equation. So you're missing a number that you've got to fill in. So on number 5, you've got log base 3 of 1/9 equals something. Well, it didn't call this anything, so let's call it x, because that's usually the variable we're trying to look for. Now, in order to solve for this x, you can't solve a logarithm in this form. I would recommend you rewrite it as an exponential equation. So right below, like we just practiced, let's write this as an exponent. Your base of 3 will become the base of the exponent. The 1/9 that is attached to it needs to go to the other side. So there's 1/9. And the x that's by itself needs to become the exponent of 3. And what you'll notice is that this now looks like some of those relating the base questions we did in the 5.1 video. This actually, I think, is almost an exact problem we saw in that video. If you remember, I would leave the 3 to the x alone, and I rewrote 1/9 as 1 over 3 squared because the 1 couldn't change, but I could rewrite the 9. And then we talked about how you can bring that 3 squared to the top and rewrite this as 3 to the x equals 3 to the -2. And since both of your bases are now exactly the same, you can set the exponents equal to each other, which is x equals -2. And so from the very beginning, this is the value of your logarithm. So the number that would have to go here to make it true would be -2. That is log base 3 of 1/9. Let's do a second one so you have it for your notes and for the video. Log base 6 of the cube root of 6. So once again, I'm trying to figure out what's missing. So I'm going to once again call that x, and I'm going to rewrite this as an exponential equation. I'm going to take my base 6, all right, the cube root of 6 that's attached to it, I'm going to move that to the other side, and the x that's not attached to it, I'm going to move it over and make the exponent. Once again, you're trying to relate the bases here if you can. So I'm going to leave the 6 to the x alone. And as you also might remember from the last video, we can rewrite the cube root of 6 since it has a power of 1. The cube root of 6 is the same thing as 6 to the 1/3. Since your bases are equal and they're both 6s, we can now just set the exponents equal to each other, which would give us x equals 1/3. And so the number that is missing from this logarithmic expression would be 1/3 for it to be true. And so that kind of shows you that you can fill in the missing pieces of logarithms by converting it to an exponential equation. All right. The other nice thing about logarithms is that there are some cancellation properties, and there's actually 4 of them. They don't always show up all the time, but I want you to be aware of what they are just in case they do, and it might save us a little bit of work. So I'm going to run through all 4 of these, and then I'm going to show you an example of each one so you have that for your notes. So the first one, if you ever run into a logarithm where the base of the logarithm and the number next to the logarithm are the exact same thing, that is fine. It's actually great for us because that means your answer will always just become 1 because they cancel each other and they end up going to a value of 1. So if the base and the number next to it match, that's great. Moving down, similarly, you notice once again, there's the base of b. There's the same b value next to it, but this time there was an x attached to that b. That's fine. We know that the logarithm and the b will cancel, but since that x is a different value, you have to keep whatever that x value is. So log base b of b to the x would just be x because the rest of those terms cancel. Moving over to the right, also talking about exponential equations, if the base of your exponent is raised to a logarithm and the logarithm of the base of that logarithm is also b, then once again, they cancel each other, but they don't cancel this x right here. So you end up with an x value on the end. I will put a little exclamation by this one. This one's pretty rare. We don't see it very often, but I just want you to be aware of it because I think we might see it once, but it is something that will help us do some work. And then probably the most popular logarithm or property I want you to be aware of is this last one. If you have a logarithm, and it does not matter what the base is, if the inside of your logarithm, or if the number next to your logarithm is a 1, your answer will always be 0. It does not matter what the base is. If the number next to the right of your logarithm is the number 1, your answer will automatically go to 0, and that will be very helpful for what we're going to see throughout the rest of chapter 5. All right, so even though some of these don't show up very often, I thought it was necessary to show you one of all 4 kinds, just so you know what you're looking for if these ever show up. So beginning with number 7 in the top left, you've got log base 5 of 5. So you'll notice that the base of your logarithm and the number next to it are exactly the same. So they do cancel each other, and this just gives you an answer of 1. Very nice, simple, sweet, and straight to the point. Number 8 is the rare one, the one we don't see very often. You've got 2 raised to the log base 2 of 57. In this problem, the base of your exponent and the base of the logarithm match again like it did over here. They do cancel, but that 57 next to it does not cancel, so your final answer is you still have a 57 left over. Moving down to number 9, you've got log base 7 of 7 to the negative 4. Well, once again, the base of your logarithm and the number next to it match like it did in number 7. So those are going to end up canceling, but the negative 4 does not get canceled with them. So you end up with a final answer of negative 4. And last but not least on this slide, you've got log base 8 of 1. It doesn't even matter what the base is. What I notice is that there is a 1 to the right, directly to the right of the logarithm, which means no matter what the base is, your answer is automatically going to be 0 for number 10. And so hopefully that shows you an example of all 4 cancellation properties. Even though we will not see them all the time, it is good to know what they are in case they do show up in problems that we see. All right, so nearing the end of this video, one of the last things I need to cover in this section is what's called common and natural logs. So similar to exponentials, we talked about exponentials in the last video, and then we moved into the e. Well, that's a special case of an exponent. There's also special cases of logarithms, and so there's 2 of them. The first one is called a common logarithm. We define a common logarithm as having a base of 10. Now, the reason this is a special one is because whenever you have a base 10 for a logarithm, we usually don't write that number 10. So as you can see in this example here, you have y equals the log of x. You do not see a base number next to it like we're used to. That's because it is understood. If you don't see a base, it is understood to be a 10. Similarly, you've seen this before when you work with square roots. You usually don't write the 2 for the square root. It's understood. That's kind of the same idea here that we're working with. The second kind of logarithm, and probably the one we'll use more in the next few videos, is called a natural log. So if the base of your logarithm is that e that we talked about in the last video, which is Euler's number, then we can rewrite this in a different way. So we don't ever write log base e of x, all right? Anytime you have a log base e, we instead write that as the ln of x. And so ln represents a natural logarithm. Now it's not NL. We write it as ln because the person who discovered this was did it in Latin, and in Latin, natural log is written as ln in its enunciation. So we will use ln of x to represent a natural log, which means the base of the logarithm is e. Now, a couple of special things that show up with especially natural logs that you might want to be aware of are down here at the bottom. The first one says, if you ever take the ln of 1, that answer is 0. That's similar to the cancellation property we saw a few minutes ago. If there's a 1 next to a logarithm, the answer goes to 0. If you ever run into the situation where an ln and an e are next to each other, that's fine. They actually cancel each other and it just goes to 1. And finally, if you ever end up with the natural log of e to the x, once again, the ln and the e will cancel each other, but since the x is not being canceled, it has to stay along for the ride. And so the ln of e to the x would just be x. And so we need to be comfortable with these special kinds of logarithms that we'll see. All right, so let's go back to our writing form, getting used to this. I would like you to write the following exponential equations in logarithmic form, but these are going to have a special case to them. So on number 11, you have 10 to the 3 is equal to 1,000. Well, if I want to write this as a logarithm, remember from earlier in this video, I will first identify my base. So the base of my exponent, which is 10, has to also be the base of my logarithm. Now, the number that is attached to the base 10, remember, we got to flip-flop the other two numbers. So that 3 needs to move to the other side, and the 1,000 needs to move right next to the logarithm. Now, if you type this in your homework, they're going to say that it's not written in the right form. That's because we don't ever write the base 10 when it comes to a logarithm. So instead, what we would write is we would write the log of 1,000 equals 3, because the base 10 is understood to be there and we don't have to write it in this case. All right, looking at number 12, you've got e to the k is equal to 2. So if you were trying to rewrite this as a logarithm, once again, identify your base. So the base of your exponent is e. So we would start with log base e, and then you have to flip-flop the other two parts. The k needs to move away from the e to the other side. So we'll put the k on the right. And I need to bring the 2 to the left and put it next to the e. Once again, if you type this into your homework, it's probably going to say you didn't write it in the right form. That's because from the last slide, when you run into a log base e, we have a special way of writing that. It is written as the natural log, or the ln. Then we'll bring down the 2 and we'll bring down the k. That is your simplified form. So e to the k equals 2 is the same thing as the ln of 2 equals k. All right, let's make sure you're comfortable going the other direction as well with these special cases. So these are two logarithms with special cases. I want you to rewrite them as exponents. So on number 13, you have log of k equals L. Now, normally I would tell you you need to identify the base, but you probably can see there is no base down here. That's fine. With a logarithm, if you don't see the base, it is understood to be 10. And then just like the other problems we've done, the other two letters, the K and the L, you need to flip-flop. So I would move the K to the other side of the equal sign, and I would move the L to the exponent of the 10. And I always write my L's in cursive, because if not, my L's look like ones. So if you're ever looking at my notes, I always write my L's in cursive. All right, likewise with number 14, you have the ln of z equals 4. So once again, you need to identify your base. Now with ln, you won't actually see the base, but what you have to know is that there is a base of e that's built into the natural log. So if I bring down the e as my base, and then once again, the z and the 4, you need to flip-flop. The z will move to the right, and the 4 will move to the exponent of e. And so the ln of z equaling 4 is the same thing as e to the 4 equals z. And so even though these are special case logarithms, we still follow the same rules that we covered earlier in this video. All right, and finally, the last property of logarithms I need to cover in this video to wrap it up is domain. So with exponential functions, we talked a little bit and very briefly that exponential functions have a very easy domain. They go from negative infinity to positive infinity, but logarithms are not that way. So when you are trying to find the domain of a logarithm, so in the little box on the right-hand side of your screen, if f of x equals log base b of a function, g of x, if you are being asked to find the domain of f, what you will have to solve is you will have to actually set up an inequality. You will have to take whatever is inside the logarithm, in this case we're calling that g of x, and you must set that to be greater than 0. That's because with logarithms, you cannot have a 0 or a negative number inside of them. So we have to force the inside to be greater than 0. So on my two examples on the left over here, it says to find the domain of each. Now, on number 15, it says f of x equals the log of negative x. With domain, it does not matter what your base is. It doesn't matter even if it's a special case. All we care about with domain of logarithms is you will take whatever is inside, which is negative x, and you will make that greater than 0, and you have to solve that inequality. So on this one, I would divide both sides by -1. And if you remember back in chapter 1, when we covered inequalities, whenever you divide by a negative number, you have to switch the inequality, and 0 divided by -1 is 0. So we have to write this in interval notation. So remember, if x is going to be less than 0, that means the smallest number I know that's less than 0 would be -infinity. And then we would go all the way up to 0 in this case. Now we know that the infinity gets a parentheses by rule. And in this case, the 0 will also get a parentheses because there's not an equal sign on the inequality. And so that is the domain of your logarithmic function here. We can do the exact same thing for number 16. You've got f of x equals the log base 1/4 of 2x plus 6. Once again, I don't care, and none of us should care what the base of the logarithm is, because it doesn't change how we work the problem. All we're going to do is take what's inside the logarithm, which is 2x plus 6, and you're going to make that greater than 0. And now we're going to solve this. So I'm going to subtract 6 from both sides to give me 2x is greater than -6. And then I'm going to divide both sides by 2. And you're going to have x is greater than -3. So to take this inequality and write it as an interval, if x is going to be greater than -3, that means the biggest number you can get is infinity, because it would go on forever, and our lowest number would be -3. The infinity by natural situation gets a parentheses by rule. And then since there's no equal sign, the -3 will also get a parentheses. And that gives us the domain of number 16. And so it doesn't matter what the base is. If I ask you to do a domain of a logarithm, you just take the inside and you make it greater than 0 and solve. So that wraps up my video for section 5.2. This covered the idea or basic idea of what a logarithmic function is. And then we also covered some of the basic properties of logarithms as well. In the next video, we're going to continue our discussion about logarithms, and we're also going to start mixing back in some of the exponential stuff, because both of these types of functions work naturally together.